I'm going to tell you about these detections that we reported in the paper about a year and a half ago of methyl chloride in protostellar and cometary regions, and also about the ongoing lab work that we're doing at JPL to support this detection and maybe guide future observation to observe more of these species. So first of all, why methyl halides? Well, these species are abundant in the atmosphere of the Earth. So a couple of decades ago, they were mainly found because of industrial processes. But these days, they're actually, the main production source is actually for biological processes. So, for example, metabolizing allergens into the oceans by algae, and they will reject organohalogens into the atmosphere. And due to this connection between biology and for these species, they were proposed as potential biomarkers if observed in the atmosphere of exoplanets. This was further supported by the fact that in the interstellar medium, well, we actually detect halogen species, but very small ones, so HCl, HCl+, and so on. And most of the halogens, especially for chlorine here, is actually found in the diffuse interstellar medium and not into molecular clouds where star formation is happening. So the question that we have is there an actual disconnect between the halogen chemistry and the organic chemistry that we see in star forming and planet forming environments? So to figure this out, we searched for them into protostellar environments, and specifically within the framework of the PILS program, that is an ALMA program. So ALMA looked at the rotational lines towards a low-mass protostar here for this PILS program led by Jes Jorgensen. So this protostar, RS16293-2422, is actually thought to be an analog of what our sun looked like when it was forming. So we looked at rotational lines nearby one of its sources, source B, around 16293. And within this large program, we actually covered a large frequency range at a very nice spectral resolution that allowed us to look at these lines, and also at a very high angular resolution, 0.5 arcsecond, which for the sources correspond to about 60 AU. It's actually very small for a protostar. So this is what the data look like. So it's lots and lots of lines. It's actually a spectrum that is taking at one spatial, extracted at one position towards the star. We actually have a whole map of these. And all of these are rotational lines from molecules. And most of them are like molecules that we know, that have been observed before, like methanol, dimethyl ether, and so on, deuterated version of these. But some of these lines are actually due to molecules that haven't been identified before, and this was the case for methyl chloride. So this is what we found. This is the detection that we got. So for the 35 chlorine and the 37 chlorine, as you can see, the lines are like very intense. We can actually, detect them up to K equal 4 into this 13 to 12 transition for this symmetric top molecule. So nice, we can fit them, we can derive column density for these two species, and by doing the ratio of 35 chlorine over 37, we actually find 2.1 in this star forming region. So for those of you who are familiar with the value of isotopic ratio for chlorine in the solar system, it's going to be a bit of a surprise. In the solar system, we expect a value of 3.1. But it's actually not surprising to find 2.1 because previous detection of HCl found this ratio to be 2.1, and it's actually now accepted that this ratio changes in different molecular clouds nearby our solar system. So this is what also, so combining these two abundances and comparing them to that of methanol, one of very ubiquitous organic molecule in this region, we found a ratio of about 10 to the minus 4. So methyl chloride is not an abundant species in this environment, but it's not negligible either, and we see it here. I'm showing you here the emission of methyl chloride around this protostar, so shows B here, and this actually, the spectrum that I show you here was extracted at this position to here. So we detected this methyl chloride around a low mass protostar, and some of the members of the PILS team were actually also members of the Rosina team that looked at the outgassing of Comet 67P. And so we asked them to look in the spectra of Rosina, and especially the DFMS, to see if we would find this methyl chloride, and it was actually there. Have a small shoulder here around mass 50. So the resolution of this mass spectrometer is such that you can disentangle different isomer at one specific AMU. We can disentangle for different atomic composition, and that's how we could get this methyl chloride detection. We see the 35 chlorine. We don't see the 37, but it's not surprising if you accept this 3.1 isotopic ratio for chlorine in the solar system. What is interesting is to look at the abundance at which we observed methyl chloride versus methanol around 67P. And we found 10 to the minus 4, which is similar to what we've seen for the protostar. And this supports the scenario of an inheritance of chemistry formed in the protostellar regions that would be inherited down to comet-forming regions, or at least a scenario where the chemistry is similar in these two environments. So the question is, how do we form methyl chloride? How does it get here? And well, we don't know yet. But astrochemical models actually took a crack at it after this detection was published. And they actually found that you could form a methyl chloride efficiently by chlorination or hydrogenation of carbon of methyl onto the grain surface that you find in the protocellular envelope. So you form CH3Cl, and then the grains in the outer part of the protostellar envelope flow towards the central object when it's forming. And so the grains warm up, and molecules that you would form into the ice surface will dissolve in the gas phase and be able to, that's how we can detect them with radio interferometers. Of course, this is the theory, this is what the models tells us, but we need to perform laboratory experiments to figure out what is the actual formation mechanism. But before doing that, what we also need to know is how to quantify methyl chloride in the solid state if we want to test this formation scenario. And for this, so we need to do laboratory study, and specifically looking at spectroscopic studies, because spectroscopy is the main tool that we have to look at molecule formation in the solid state, so infrared spectroscopy in the mid-IR. So that's what we're currently doing. So it's ongoing work at JPL that we're doing, so looking at the spectroscopy of these methyl halides, so in pure ice films in this case, and what we would like to know is to derive band strength for the different vibration of these molecules in the solid states. So here I'm showing you the spectra that we get by depositing molecules, so CH3F, CH3Cl, CH3Br, or CH3I onto cold substrates, interrogating the spectroscopy with Fourier transform and Fourier spectroscopy. And as you can see, well, we can attribute the emission, the vibrations. So for the CH stretching and the CH3 deformation here, there's not a huge change between the different types of halogens, but of course, once you go towards CH3 rocks or CX, so CF or CCl stretch, there's a clear changes due to the presence of the halogen and the nature of the halogen. To get the band strength, what we're doing is that we're integrating the optical depth under these bands, divided by the column density of ice that we deposited, and this is what we report here. I warmed up the ice at different temperatures, and as you can see, the band strength for different CX stretch and CH3 rock does not really change with temperature. I mean, there's a decrease here for CH3 at high temperature, most likely due to the onset of desorption. But what actually changed is the shape of the features that you get. So this is what we get when we deposit these films at low temperature, and when we increase temperature, we have very different shape, most likely due to the crystallization of these films. In water ice, we also observe the change with temperature here that is most likely due to the diffusion of molecules. So here it's a water to CH3I 10-to-1 mixture. At high temperature, you can have diffusion. These molecules likely segregate, and that's why we can observe the signature of crystallization. So we get this band strength. Another characteristic, another behavior of these ice films that we're highly interested in would be to look at the thermal desorption of these ices. And that's what we've been doing this time by depositing ice film onto not a window, but into a cryogenically cooled microbalance. So we deposited them, different ice films of different thicknesses. And what we did with the microbalance is to follow the ice loss versus temperature and looking at the derivative here, so ice loss rate versus temperature. What you can see is that for the different thicknesses, well, the rate does not change. This is typical of a zero-order desorption kinetics. You can fit these rates by this equation, extracting here the desorption energy, so the desorption that you need to overcome to have desorption occurring. These are the energy that I get. As you can see, there's not a clear correlation with the mass. CH3Cl is a bit out of the way here, and it's most likely because not just the mass is involved into the desorption of this species, but also other parameters such as the polarity or even the size of these molecules. CH3Cl here is really standing out. Could explain this, like the dipole moment here, and could explain why it's stickier and it takes more energy to desorb. So pushing further towards astrophysical implication, we can use this sublimation energy that we derived in the laboratory to measure, well, predict and derive where the desorption fronts of these species are going to be in around protostars. So derive where the snow lines are going to occur. And that's what I've been doing here with quick calculations. So the definition of the snow line of the desorption front is where the flux of adsorption equals the flux of adsorption equals the flux of desorption. By equating the impingement rate of the atom of the molecules equals to desorption rates. You can derive this temperature here, which for this species, using typical abundances, gives you the following temperature around the protostar. And by using this temperature and a temperature profile around protostar, so here it's actually the profile for 6293. We observe methyl chloride, you can actually predict that methyl chloride, pure methyl chloride, will desorb around 130 AU from the central object. It's going to be further out for methyl fluoride and closer for the other methyl halide. What's interesting to see also is that the 130 AU value that we get is actually quite close to where we detect this methyl chloride here with ALMA. The beam that I show you here is about 60 AU. And it actually corresponds to here where two beams, where here we have this onset of desorption when you start to see methyl chloride popping up into the gas phase. All right, so that leaves me to my conclusions. So I showed you detections of methyl chloride around protostar and around a comet, really showing that there's a link between the organic and the halogen chemistry in interstellar environments. These molecules are not direct biomarkers if observed in the atmosphere of exoplanets. However, we need more detection to figure out what is the standard, the regular, typical amount of these compounds in interstellar environment to see if an exoplanet would have differences in abundance. Through the spectroscopic experiments, we saw that the CX and the CHRX were highly depending on the type of methyl halides that you have, and their shape depends on the temperature of the ice film, so they can be used to probe the ice environment. We also derive band strength that now can be employed to quantify the formation of these species in ice films. The desorption energy showed us that they're not strictly correlated to the mass of the species, that other parameters are involved when measuring desorption energy of molecules. You need to look at effects like size of polarity. And the calculation of where the sublimation front would be showed us that it's in agreement with what has been observed by ALMA, but the search for CH-red, which it didn't detect yet, is going to be much more complicated since it's dissolved further out and the Coulomb densities are expected thus to be lower then. All right, so this is it. Thank you for your attention.